Welcome to the Tech channel. In this session I will go through 15-star method interview questions and answers focused on scalability design patterns in payment solution architecture. You can watch first 4 question pattern. Remaining questions you can download from the link provided in the description. Question 1. Horizontal scaling implementation. Describe a time when you implemented horizontal scaling for a payment processing system. Situation. Our payment gateway was running on a single monolithic server handling 15K transactions per second, TPS, during normal hours. During Black Friday, traffic spiked to 45K TPS, causing server CPU to hit 98%, response times to increase from 200 milliseconds to 8 seconds, and ultimately resulted in 2 hours of degraded service affecting $3 million in transaction volume. Task. As lead architect, I was responsible for redesigning the payment infrastructure to support 100K TPS during peak periods, ensure sub-200 ms response times under load, provide linear scalability to handle future growth, and implement zero downtime deployments. Action. I architected and implemented a comprehensive horizontal scaling solution. Refactored the monolithic application into stateless microservices enabling independent scaling of payment authorization, settlement, fraud detection, and notification services. Deployed AWS Application Load Balancer, ALB, with session affinity disabled to distribute traffic across application instances. Implemented auto-scaling policies based on multiple metrics, CPU utilization greater than 70%, request count 500 instance, response time greater than 150 milliseconds, scale-out triggers add to instances, scale-in after 10 minutes below threshold. Migrated session state from in-memory to Redis cluster, 3 master nodes, 3 replicas, for shared state across instances. Configured health checks with graceful shutdown, health endpoint checks, 30-second deregistration delay, drain existing connections before shutdown. Implemented database read replicas, 1 primary plus 5 read replicas, with read-write splitting at application layer. Deployed across 3 availability zones for high availability. Created comprehensive monitoring dashboards tracking instance count, per instance metrics, scaling events, and cost optimization. Result. Successfully scaled to handle 120K TPS during next Black Friday with zero downtime. Average response time maintained at 145 milliseconds even at peak load versus 8 seconds previously. Autoscaling reduced infrastructure costs by 40% during off-peak hours by scaling down from 20 instances to 6 instances. The system automatically handled a DDoS attack by scaling to 45 instances, absorbing the attack without service degradation. Deployment frequency increased from weekly to multiple times per day using blue-green deployments with zero downtime. Question 2. Multilayer caching strategy implementation. Question. Tell me about implementing a multilayer caching strategy for a payment platform. Situation. Payment platform experiencing database bottlenecks with 80% of load from repeated queries for merchant configs, exchange rates, and fee schedules. Database queries taking 150 to 300 milliseconds during peak times, approaching 1000 connection limit, unable to scale beyond 25K TPS. Task. Implement comprehensive caching strategy to reduce database load by 70%, improve response times to under 50 milliseconds for cached data, support cache invalidation for updates, and enable scaling to 100K plus TPS without database upgrades. Action. Times deployed Redis cluster, 6 nodes, 3 masters, 3 replicas, with 48 GB memory, 500K OPS sec capacity. Times implemented cache-side pattern with TTL-based expiration, merchant configs, 24H, exchange rates, 1H, sessions, 30 minutes. Times created application-level in-memory cache, caffeine, 2 GB heap, for ultra-hot data with 30-second TTL. Times implemented CDN caching, CloudFront, for static assets with 24-hour duration. Times built cache warming mechanisms and invalidation strategy with pub/sub notifications. Times implemented circuit breaker for Redis failures with database fallback. Result: achieved 94% cache hit rate for merchant configs, 98% for exchange rates. Database load reduced 82%, 45K to 8K queries sec. Response time improved from 180 milliseconds to 35 milliseconds. Scaled to 85 kTps without database upgrades. Connection utilization dropped from 850 to 200. Prevented database overload during 10x traffic spike. Annual cost savings, $120,000. Question 3. Database sharding strategy. Describe implementing database sharding for a growing payment platform. Situation: our payment database had grown to 4.5 terabits with 25 merchants and to-be transactions. Single database performance was degrading, write operations taking 500 ms plus, backup windows extending to 8 hours, query performance deteriorating despite optimization. We were approaching PostgreSQL's practical scaling limits and needed to support 10x growth over 3 years. Task: I was tasked with implementing a database sharding strategy that would partition data across multiple databases, support linear scaling to 100 merchants, maintain query performance under 100 milliseconds, enable zero downtime migration from single database, and preserve ACID guarantees for individual merchant transactions. Action: I designed and executed a comprehensive database sharding implementation. Selected merchant_ID as sharding key based on analysis showing 95% of queries were merchant-scoped and even distribution across merchant IDs. Implemented consistent hashing algorithm, Murmur hash 3, to distribute merchants across shards. Initial deployment, 8 shards, expandable to 64 without resharding majority of data, each shard, PostgreSQL 14 with 512 GB storage, 64 GB RAM, virtual sharding concept with 256 virtual nodes mapped to physical shards. Built routing layer, Sharding sphere proxy, that intercepts all database queries, extracts merchant_ID from query, determines target shard via hash function, routes query to appropriate shard, aggregates results for cross-shard queries. Created phased migration strategy. Phase 1, set up new shard infrastructure in parallel. Phase 2, implement dual write to both old and new databases. Phase 3, migrate historical data in batches. 10K merchants are. Phase 4, gradually shift read traffic to new shards. Phase 5, decommission old database after validation. Implemented global transaction handling, local transactions within single shard, ACID maintained, distributed transactions across shards using Saga pattern, compensating transactions for rollback scenarios. Designed reference data strategy, replicate small lookup tables, countries, currencies, to all shards, centralized global sequence generators for transaction IDs, merchant-to-shard mapping in Redis for quick lookups. Built monitoring and observability, shard health dashboards, data distribution metrics, cross-shard query analysis, automated rebalancing alerts. Result: successfully migrated 25 merchants and to-be transactions over 6 weeks with zero downtime. Write performance improved from 500 milliseconds to 85 milliseconds average. Query performance maintained under 50 milliseconds for 99th percentile. Backup windows reduced from 8 hours to 45 minutes per shard, parallel backups. Each shard currently holds 3.1 M merchants A. Question 4. Asynchronous processing architecture. Tell me about implementing event-driven, asynchronous processing for payment workflows. Situation. Our payment API was processing everything synchronously: authorization, fraud check, settlement initiation, merchant notifications, and analytics updates. This resulted in 2 to 4 second response times for payment requests, timeout failures during fraud service slowdowns, cascading failures when downstream services were unavailable, inability to scale individual components independently. Task. As architecture-led, I needed to redesign the payment flow to be event-driven and asynchronous while maintaining sub-200 ms API response times, reliable processing of all payment events, ability to replay failed events, independent scaling of each processing component, and guaranteed at least once processing semantics. Action. I architected an event-driven system using message queues. Deployed Apache Kafka cluster, 6 brokers across 3 AZs, with 3x replication factor for durability, 30-day retention for replay capability, 1 M messages sec throughput capacity, topic partitioning by merchant_ID for ordering. Redesigned payment flow into synchronous and asynchronous components. Synchronous, in API response payment authorization, 80 milliseconds, basic validation, return transaction ID. Asynchronous, via events fraud scoring, settlement processing, merchant webhooks, email notifications, analytics processing, reconciliation. Created topic architecture, payments.authorized, partition by merchant_ID, payments.fr odd_checked, payments.se tilde, payments.failed, notifications.send. Implemented consumer services as independent microservices, fraud service, 15 consumer instances processing 25k events sec, settlement service, 8 instances with batch processing, 100 payments batch, notification service, 5 instances with rate limiting, 10k emails min, analytics service, 3 instances writing to data warehouse. Built idempotency handling, unique event IDs for deduplication, Redis-based idempotency keys, 24 RTTL, database constraints preventing duplicate processing. Implemented dead letter queues, DLQ, for failed events with automatic retry with exponential backoff, 3 attempts, move to DLQ after max retries, alert generation for DLQ buildup, manual retry tools for investigation and reprocessing. Created event versioning strategy to support schema evolution without breaking consumers. Built comprehensive monitoring, consumer lag monitoring, event processing latency, failure rates and DLQ depth, throughput per topic and consumer. Result. Reduced API response time from 2 to 4 seconds to 120 milliseconds average, 95% reduction. Eliminated cascading failures, fraud service outage no longer impacts API availability. Scaled fraud processing independently to 50k events sec during fraud attacks. Successfully processed 2.8 M payment events daily with 99.97% success rate. Event replay capability. A comprehensive PDF with 15-star method interview questions and answers focused on scalability patterns in payment solution architecture. You can download from the link given in the description. The document includes key features, 15 real-world scenarios covering critical payment security topics. Each answer follows the complete star format: situation, task, action, result. Topic covered. Horizontal scaling implementation. Multilayer caching strategy. Database sharding strategy. Asynchronous processing architecture. Circuit breaker pattern. CDN and Edge Caching. Autoscaling strategy. Microservices architecture migration. Read-write splitting and CQRS. Rate limiting and throttling. Multi-region geographic distribution. Connection pooling optimization. Batch processing optimization. API gateway implementation. Performance testing and capacity planning. Thank you for watching.